Now we talk about OLS. Let's start by just looking at some pictures. I got two graphs of some different variables here. Don't focus on what's on each axis, just concentrate on how the graphs are presenting the data. On the left side, you can see these data are pretty well shaped. There seems like a tight correlation. If we drew a line, there'd be a positive slope. In contrast, the graph on the right side just looks kind of random. Those are two very different sets of data. So we want to find a way to say how well a simple line can represent a whole collection of data points. A line can be a way to summarize a whole collection of dots in a more efficient way. I want to find a line that's in some way close to each value of y. Close to is typically defined as minimizing the average squared distance, the vertical distance. That's why it's called least squares, OLS, or at least that's the LS part of least squares, then it's the ordinary. Common, basic. The one that we come back to again and again and again and again, that's the O in OLS. There's a formula, but we'll circle back around to that later. First ask, well, why is this useful? It is a very powerful simplification. If I say y is some value, beta naught plus beta 1 times x plus epsilon, then if that epsilon is small, then I'm taking that whole collection of data, all those dots, all that stuff going on in the picture, and reducing it down to just beta naught and beta 1. Just two values. So it can be a really significant compression of how much data I need to keep track of. Beta 1, the slope, can be greater than or less than 0. If beta 1 is less than 0, then the slope is negative, and there's a negative correlation between x and y. If beta 1 is greater than 0, then the slope is positive, and there's a positive relationship between x and y. If beta 1 is 0, then there's no relationship between x and y. A negative relationship is not the same as a zero relationship. Example I sometimes use is remember when we were a rebellious teenager, doing exactly the opposite of whatever our parents told us to do. We might not have quite realized it, but we're not showing independence. If, when someone tells you to do one thing, you always do exactly the opposite, in fact, you're being completely determined by the other person. Only if there's a zero relationship are you independent. Sometimes you do, sometimes you don't. You make your own choice. That's a zero relationship. Estimating a beta 1 equal to 0 would be a case where there's no relationship, such as the line in the graph there. Given some value of x, predicted y value is going to be just the average value of the y's conditional on that x. Here are the same two pictures now with a regression line drawn through them. You can see there's a positive relationship in one case, while the other is pretty much 0. But how can I tell the difference? There are lots of possible criteria. One could just be an aesthetic judgment, which I don't want to throw out as completely straw man because it's actually not entirely relevant. There are cases shading into the next consideration. Is it persuasive? If it looks lovely, then perhaps it can be good at persuading somebody. You can also ask, is it useful? That is sometimes slightly different rationale than being persuasive. Can ask, is it precise? That's equivalent to asking, how big is epsilon relative to the other terms? That is a bit easier to measure and formalize. It's useful to keep in mind these are each going to be distinct questions. We're going to have a lot of measures to say how precise is this, but that doesn't necessarily provide a judgment about is it persuasive or is it useful. One of the questions we'll ask is, how can we guard against being fooled? Against thinking maybe there's a relationship. Maybe it looks like the dots are kind of wiggling together in some way, but they're not actually. Maybe I'm just being fooled. People draw constellations in the night sky. Sometimes it looks like the stars just line up in a row, and we humans draw a line. Ancient people thought that some gods put that line of stars there to communicate to mortals. But the apparent locations of stars are entirely random. So how do we guard against being fooled, against seeing lines that aren't really there? That's what I call the thinking like a statistician. We ask, what if the slope were truly 0? What kinds of things would I see in that case? What would be a surprise if there were no relationship? What would surprise me? Oh, I thought it was a 0, but it's kind of weird to see a line. Let's go through a little experiment. Here we have y equals 10 plus 2x plus e the error, but the error is really large. That's the plot there. You could put a line through those dots. Reasonable people could argue about what kind of line that would look like, but the line that minimizes the squared vertical distance has a slope of 1.61813. Okay, how do I guard against being fooled? What if actually there was a zero correlation? What if the true value of beta 1 were 0? I could still randomly get some y values that might produce a slope that's not 0. I estimate a slope on these actually genuinely uncorrelated values. Maybe do that 10,000 times just to see what results I get. Histogram shows the estimated values of beta 1 from 10,000 simulations. We see that most common result is near 0, but a tiny fraction of the 10,000 gives values as low as -3 or as high as +3. I can see my original estimate of 1.61813 is a bit of a distance away from 0. Only 659 out of 10,000 gave a slope estimate that was that big or even bigger. That'd be a p-value of 6.59, which is not greater than 5%, so we would not reject the null at a 5% level of significance. Now, hopefully some part of your brain is now firing neurons. Hey, that looks kind of like the dice example. Yep, same framework. Under a pretty general set of conditions, the OLS slope coefficient has a normal distribution. Thus, the estimate of beta divided by the standard error of beta is going to have a standard normal distribution. We often call it the t-stat, or t-statistic, because if n is small, then it's a t distribution. But in most cases we're going to be working with here, we'll have a lot of observations. It's a standard normal distribution, but still called a t-stat. To test against the null hypothesis of 0, which is the most common, we would form the test statistic as beta hat minus 0 divided by the standard error of beta. If we want to test against some other value, not 0, then we put that in. But it's very common, normal, really. Sorry, bad joke. It's really common to test against 0 because that's a sign of no relationship. If there were nothing going on between x and y, no correlation, no relationship at all, then I'd expect to see a value near 0. Thus, most computer programs automatically calculate a p-value against the null hypothesis of 0. I explained this earlier. We can talk about the estimate, we can talk about the p-value, we can talk about the confidence interval. Any of those, they have the same ultimate relationship, and we're making the exact same statistical tests. They're just different ways of saying the exact same thing. It's super easy to calculate t-stats and p-values, so most computer programs just spit them out automatically. For univariate regression, where there's just one x variable, the statistical significance for the slope coefficient is the same as statistical significance for the overall regression. Next, we're going to add in more x variables, and that will drop away. To get these easy interpretations, there's inevitably some cost. The cost for this easy result of OLS is we have to make some assumptions. The biggest, hugest, most critical assumption is the first one, that x completely specifies the causes of y. There's nothing omitted, nothing else going on. Y is determined by x and some completely random error, and there's nothing else. That is a really strong assumption. It's a big deal. One of the reasons we'll often add more x variables is because of that. We also have to worry, might there be some reverse causation? Is there a reason to think that y is going to cause x? We could also assume that x causes y in a linear manner, which is why we're drawing a line. A line is linear. We also assume the errors are normally distributed, which is especially crucial for cases where we have small degrees of freedom. If we have more observations, then we can get away with slightly looser restrictions. Then we assume the error and the x variables have fourth moments defined. That's pretty typical. Next, at least at the beginning, we assume the errors all have the same standard deviation we call homoscedasticity, or that the errors are not heteroscedastic. There's no heteroscedasticity. Yeah, those are big words. Mostly just used for impressing outsiders. Finally, we assume the errors are going to be all independent of each other. I might imagine cases, particularly in a time series, where the miss in one direction means you might expect to see a miss in the opposite direction next. But with all these assumptions, we can say that OLS estimators are unbiased and consistent, In fact, they are BLUE, B-L-U-E, Best Linear Unbiased Estimator. Which sounds impressive, except it's the best among the rather small category of linear unbiased estimators. It's kind of like saying somebody is the best looking economist. It's not such a big statement as you might like to think. We do have some formulas, though you don't really need to know them since, of course, the computer takes care of all that. But we'll talk a bit about how the formulas are derived. We have a simple problem set up as yi. That's a whole list of y values from 1 to n. And that's equal to beta naught plus beta 1 times xi plus some epsilon. The y and x are known, and we're going to choose beta naught and beta 1 to minimize the errors. Now from calculus, you should remember, how do I minimize something? I take the derivative and set it to 0. Easy. And that's one of the big reasons we have squared errors here, because taking the derivative of a squared term is pretty easy. If we wanted instead to minimize, the absolute value of the errors, then you could. Except taking the derivative of the absolute value is a pain in the ass right around 0, which is where I want the errors to be. That certainly can be done, but historically that would take more computing power. Least squares has been around for centuries because people could do it without computers. So with some calculus, I want to minimize the squared error values by choosing values of beta. There are a bunch of steps, but it's not conceptually difficult. Find beta 1 is going to be the sum of x minus x bar times y minus y bar divided by the sum of x minus x bar squared. The key thing to note in that formula is the top looks very similar to the formula for covariance. The whole formula looks like the formula for correlation, except not quite right. Correlation would have an additional y minus y bar squared on the bottom. This formula is a covariance divided by the variance of just x. One reason we might have trouble getting a good estimate of beta 1 is if the variance of x is really small. We'd be dividing by a number close to 0, which is bad. Then to some extent, the intercept term is almost just a nuisance parameter. Just calculated to make the rest of the regression work. Doesn't necessarily have too much meaning in and of itself. Makes the average error equal to 0. The beta 1 hat term is the slope, dy dx, or delta y delta x, all that stuff you learned back in algebra class when you were an infant. You get predicted values of y by putting in the estimated values of the coefficients, multiplying that by each x value. It's all enormously useful, and it's called ordinary least squares, OLS, because it's just so ordinarily done. So useful as a first step. Not commonly the last step, though. We'll talk more about some next steps.